Hey, so today we're going to be talking about rocket nozzles. Not the engines, but the nozzles. Modern rockets use the convergent-divergent shape, which was invented by Gustave de Laval. Now, Gustave invented this convergent-divergent setup in 1888 for use in a steam impulse turbine. Robert Goddard, known as the man who ushered in the space age, was the first person to adopt this to his rockets around 1915. Modern rocket nozzles are all a form of de Laval nozzle. So this converging and diverging nozzles allows us to achieve the highest velocity exhaust out the back. Now I want this because the higher the velocity of the exhaust, the more thrust that is generated upwards. So this is achieved by first increasing the velocity to the throat. This is done by constricting the flow, which we know increases the velocity of something. You can see this as you pinch the end of a hose. Now, once it becomes supersonic in the throat, it becomes a compressible fluid. So now to further increase the velocity of a compressible fluid, we now need to decrease its density. To do this, we enter the diverging nozzle. And as the density decreases, so does the pressure while the velocity increases. If supersonic speeds are not achieved in the throat, and we do not become a compressible fluid, then once we diverge, we'll just decrease the velocity even further. And we will generate no thrust, and then we will not get off the launch pad that way. Now I will let Eager Space explain a little bit better than I have.
In the combustion chamber, we have the highest temperatures and pressures, which makes sense, as that is where the combustion is taking place. The velocity is what is termed as low, which means less than the speed of sound. The constriction of the throat results in reduced temperature, reduced pressure, and an increase in velocity, up to the speed of sound. After that, the expanding nature of the nozzle results in a drop in temperature and pressure and a large increase in velocity. Here's a nice little graph from Wikipedia that shows how the pressure and temperature go down and the velocity goes up. This velocity increase is one of the main jobs of a nozzle. The faster our exhaust velocity, the less fuel our engine uses to generate a specific amount of thrust. And therefore, the more you can expand the exhaust, the higher the velocity, and the better your engine works.
So now that we know how a de Laval nozzle accelerates the gas to create a high thrust, let's talk about a couple different shapes of nozzle. Here you can see a picture of the space shuttle nozzle during a test firing sequence. As you can see, it is the bell nozzle. You can see this from the curve that gives it its bell shape. Now the curve is unique because it actually starts to converge the exhaust again. Now this is important because we want it to be a column of exhaust. The straighter the column, the more thrust and efficient the engine is. Remember how I mentioned in the diverging section that the pressure decreases? This is important, and here is why. If the exit pressure is lower than the ambient pressure, then it is overexpanded. The exhaust is underexpanded if the opposite is true. You can see how the streamlines are now angular. This decreases the thrust in the vertical section because now there is a horizontal component to the velocity vector. So hopefully we all know that as you increase in altitude, the atmospheric pressure drops. So only a minute after liftoff, you go from 1 to 0.4 bars. By 2 minutes, you are 33 kilometers up and basically in space at 0 bars. So now the bell shape that was so efficient at sea level no longer is as efficient at higher altitudes. This is why most rockets have a second stage with what is known as a vacuum nozzle. Here you can see different vacuum nozzles. You'll notice that they are basically just a cone nozzle. While they still diverge, they no longer converge back on themselves. Now here we will learn why we don't want an overexpanded exhaust, explained better than I could.
We're running a vacuum nozzle at sea level. It has a low pressure. Let's just say it's 0.4 bar. The atmospheric pressure outside the nozzle is 1 bar, and that high pressure allows a reverse flow of air to creep up inside the nozzle. The term for the situation is overexpanded. The nozzle expands the exhaust more than the optimal amount to match the outside air pressure. Here's a simulation of what happens. First, you can see that the smooth flow is attached from the wall of the nozzle. This is known as flow separation. It results in the black, chaotic shock waves you can see inside the nozzle. This is a serious case of flow separation that will probably break your engine.
Here's a picture of both vacuum and bell nozzles next to each other. You'll notice that the bell nozzles are often much larger than the vacuum nozzles. So here's the bell nozzle for the Rocketdyne F1, which was used for the Saturn V rockets. It was the most powerful single nozzle liquid fuel rocket engine ever used. The nozzle was so massive it said you could park a Jeep under it. Here is a quick video of the Saturn launch so you can see the exhaust coming out of the nozzles. So as you can see, the flames coming out basically in a straight line, and that's what we want. I hope you enjoyed a brief education on rocket nozzles. Hope you can appreciate the nozzles as much as I do, because without the De La Velle nozzle, we probably would never have reached space.